Let's look at atomic radius. And you need to know both the group trend, and the group trend is going up and down. So the group trend would be starting up here at lithium and going down. And so you can see that as you go down a group, the atomic radius gets larger. So sodium is larger than lithium and potassium is larger than sodium, right? Then after we go through the group trend, we're going to go through the period trend, which is going across. And as you can see, going across a period on the periodic table, this is period number 2 or row number 2, you can see that the atoms tend to get smaller. Right? So we're going to look at those both trends one at a time. So let's look at the group trend first. So to first look at lithium, let's compare lithium and sodium. And I have a different slide with those compared. So, all right, let's look at both of those. So now we can see that sodium is larger than lithium. And the first thing to look at is that sodium has 1, 2, 3 energy levels with electrons in it, where lithium only has 2. And so you can see going down a group, every element you go down, you're adding a whole nother layer of electrons. And so if you go back and you look at the picture I had before, if you look as you go down, look at potassium, how it has one more layer than sodium. So every element you go down, you get one more energy level of electrons, and so the atoms grow bigger. And so as you go down, the elements tend to get larger because you're adding another energy level. So that would be an important thing to know if you're trying to explain why they get larger. Every time you go down, you're adding another energy level. All right. Now, some people might question and say, well, hey, the nucleus on lithium is smaller than the nucleus on sodium. And they might say, well, hey, shouldn't sodium's nucleus with its 11 protons pull on the electrons more than lithium's 3? Well, the answer is it would, except there's this thing called the shielding effect. Let me show you what I mean by that. All right. So lithium, its 3 protons, 3 positive charges, are attracting these electrons. All right. Now, the nucleus is shielded from this outer electron here. There are 2 electrons that could, like these electrons could move around over here, and they could get in the way and block this outer electron from the nucleus. But lithium only has 1 energy level of electrons that shield the outer ones. Now, if you look at sodium, it has a more powerful nucleus because it has 11 protons. But sodium has these 2 electrons here, and there's 8 here if you count all of them. All right, so it has basically 10 electrons that could shield this outer one from the nucleus. So that lets sodium's outer electron exist further away from the nucleus. That offsets the nucleus being stronger. Okay, sodium's nucleus is stronger, but the shielding effect offsets the stronger nucleus. So the shielding effect is when you have inner electrons shielding the outer electrons from the nucleus. So the shielding increases going down, going down a group. And basically what that does is that lessens what's called the effective nuclear charge. That lessens that. So now if we go back and we look at lithium versus sodium versus potassium, look at how much shielding potassium would have. This outer electron is shielded from a whole bunch of electrons, so it's really shielded from the nucleus. So this nucleus cannot attract that very further outmost electron very well, so it exists a lot further away from the nucleus. Okay, so going down, you're adding a whole nother layer of electrons, and the shielding effect allows the electrons to exist further from the nucleus. Now, let's look at a period trend. A period trend is going across. So here I'm going to go across with lithium, beryllium, and boron. And we're going to try to explain why the radius shrinks as you go across. All right? So let's compare, I guess, lithium, beryllium, and nitrogen. Okay, so lithium has 3 protons, beryllium has 4, nitrogen has 7. Okay? So as you go across, the radius gets smaller. The main reason that it gets smaller is that as you go across the period, the effective nuclear charge increases. Charge increases going across. All right? Why does it increase? As you go across, you're adding protons. So if you look, nitrogen has 7 positive charges pulling on these outer electrons. So it's going to pull them in closer. Whereas lithium only has 3 positive charges pulling on a positive electron. Now some people might say, oh, hey, what about the shielding effect? Well, if you look, the shielding effect is the same as you go across a period. See, lithium has 2 electrons that could shield this one. How many does beryllium have that could shield this one of these outer ones? See, beryllium only has 2 electrons also that could shield one of these. Nitrogen only has 2 inner electrons that could shield the outer ones. So shielding is never a factor in period trends. So shielding is never a factor in period trends. And the reason is, in period trends, the shielding is always exactly the same. You can count the electrons. Okay, the shielding is constant going across, so it's never a factor. All right. So why do they get smaller as you go across? Well, the answer is the effective nuclear charge increases as you go across because you're adding more protons into the nucleus. The protons pull the electrons closer to the nucleus. Nitrogen has a more powerful nucleus than lithium. It allows nitrogen to pull its electrons closer. All right? So that's the period trend. Now, just going back and reviewing a little bit, if we look at the trends overall, the radius tends to increase going down because you're adding more layers of electrons, and the shielding effect basically cancels out more protons being added to the nucleus. And then going across a period, they tend to get smaller. The radius increases going from right to left because as you go across, the increasing number of protons pulls the electrons closer. Shielding is never a factor. That's it. I don't know how to stop it. All right. Okay. Does that make sense to you?
Yeah. It's kind of a lot, though.
Yeah. That's why. Atomic radius.